Welcome back to che531. In the last video we talked about implicit trapezoidal method, which is the same as Adam's Molten method, and that is where we do the average of the derivative when we discretize the equation like this. So we talked about this already. In this video I'll show you the script, how you can basically assemble the matrix and how we can solve for the unknowns. So this is the matrix we got last time, and we said because this is linear we don't need to do any iteration. I mean, in just one iteration we solve for a whole set of unknowns y2 through yn. Okay, so all we need to do is we need to assemble this matrix and solve for y using backslash operator. Okay, so let me show you the script. So this script is also on Blackboard. Okay, so I'm showing you the implicit trapezoidal method or the Adam Molten method. So the initial part of it is basically to create the matrices. Well, initially we start everything by 0, but in the next part of the script we fill up the elements that we know. Okay, so we know that because we have y1 to yn and only y1 is known because that's the boundary condition, we have n-1 unknown. So my matrix is basically n-1 by n-1. And the right hand side is also n-1 by 1. Okay, so given that I have 20 points, let's say, along the x-axis, I can create my x vector. Then the delta x is going to be the difference between the x values. I set the tolerance, the maximum number of iteration. I know the exact solution, I just have it here to compare how much error we're making using, Adam Molten's method. Okay, and that's the boundary condition at x equal 1. At x equals 0, y is equal to 1. Okay, so this part is actually constructing the matrix of coefficient. And by matrix of coefficient, I mean this matrix. So on the diagonal, you see that we have 1 minus delta x over 2 times x2 raised to the second power. On the diagonal for the third row, we have 1 minus delta x over 2 and then x3 to the second power. So note that this index actually goes up by 1, so 2, 3, 4, and so forth. Okay? Now on the sub-diagonal, I get negative of 1 plus del x over 2 and then x2. Then this is x3, and so forth. The other elements are all 0. Okay? So given that, I can basically construct the same thing in my script. I say, okay, so for row 1, I only have one non-zero element, which is 1 minus del x over 2, and then times, actually this is for another problem. Let me just go back to the problem I'm looking at. Alright, so this is the code for implicit Adam's Molten method. Alright, so again, the first part of it is to create the matrices, initialize them to 0, put the boundary condition at x equals 0 and y equal 1. Then for the first row, we only have the diagonal element, which is 1 minus del x over 2 times x1 raised to the second, x2 raised to the second power, and that's exactly this element, right? So on the first row we only have one non-zero element, and the second row we have 2. So on the second row we have minus 1 plus del x over 2, and then x2 to the second power. This is x2 2 to the second power, but there's a minus sign here, and that's exactly what we have here. X2 here, and I believe this should be X2. Let me just make sure that we have the same thing. Yeah, so okay, this is actually -1, and this is just IP. Okay, so for the row 2 down, we have -1 plus del x over 2, and this is going to be x2 raised to the second power, and then this one is x3 raised to the second power. Note that when I'm at row 2, my I row is equal to 2, and so IP is equal to 3, according to this equation. So this is going to be x2 second power, and then this is x3 raised to the second power. That's basically what I have here. So the first one is x2, the second one is x3. And the next row, I have the first one x3, the second one is x4 in the same row. And so that's why this is one index less than that one. Okay, so this creates the A matrix, this creates the B matrix. For all rows I have 0 except for row 1, which I have 1 plus del x over 2, and then this is x2 raised to the second power times y1. And that should be right here. So my first B is going to be 1 plus del x over 2, x1 raised to the second power times y1. And this should be, so when I row is equal to 1, IP is equal to 2, so actually this should be -1 as well. I'm sorry, no, this is actually right, this one should be -1. Because when I row is equal to 1, IP is equal to 2, then this should be x1 raised to the second power times y1. And that's what I have here, x1 raised to the second power times y1. Okay? And that should be the plus sign, that's plus sign, right. Right, so this actually assembles the A matrix and then the B vector. Then we do the back// operator, we solve for y. And note that this y starts from y2 because we only know y1 as the boundary condition. We don't know the rest of it. So we solve for, and as you can see here, we solve for y2 to yn. Okay, so after we solve for y2 to yn, then we already said y1, which is the boundary condition. So now we can go ahead and plot the figure. So we're going to plot y against x with red color. And if I run the code, so Atom Molten is the red line, and blue line is backward Euler, which we're going to talk about in a minute. And the black line is backward difference, second order, which is right here. We're going to talk about it in the next few minutes. Okay, so this was Atom Molten, that's implicit method in its second order. Okay, so now let's look at implicit backward difference. This is another implicit method. So this time, instead of using Atom Molten, I'm using another scheme, basically to discretize a differential equation. And so I'm going to use a table actually to discretize my dy dx. So there's a table that I already posted on Blackboard. This is the summary of the derivatives. And there are two tables here in this PDF. One table is on first order correct approximation for derivatives, and the second table is the second order correct approximation for derivatives. So this is basically O delta x, and this is O delta x squared, so hopefully this is not confusing. If you want to use O delta x squared method, then you have to look at this table. If you want to look at O delta x method, then you have to look at this table. Okay, so these two are forward differences, backward differences, and there's no central difference version for first order or for O delta x method. It means O delta x methods are only forward-backward difference. We do not have any central difference of O delta x. The first thing we have is actually second order. Right here, it's second order. Okay. So if you're looking for forward difference, the way you discretize the f prime is by fi plus 1 minus fi. I think this is clear, and it's forward, because this index is 1 more than that. If you want to do the second order derivative, you want to discretize the second order derivative, then use this equation. So this is first. This is second order derivative discretization. This is first order derivative discretization. Okay. And the same thing for backward difference. For backward difference, we have first order derivative, second order derivative. And by the way, there's a typo here in the index, should be I minus 2. So this is I minus 1, I minus 2. And same thing with second order approximation, you always have a first order, second order, depending on which derivative we want to use. We have to use the corresponding discretized equation. Okay, so let's do one example together. Let's say I want to discretize my first derivative using second order backward difference. So I go to this table and look at second order first, backward difference right here, and I'm discretizing the first derivative, so it should be this. So it's 3i for I minus 1 plus I minus 2. Okay, so 3i minus 4i minus 1 plus I minus 2. And that's what I have actually in the notes right here. 3, let's say this is I, minus 4 I minus 1, because this is 1 less than that, and then plus I minus 2. Again, this is 2 units less than that. Okay, so the relative index is important, not really the index. So if this is I, this is 1 less than that, and this is 2 less than that, divided by 2 del x. Now I should have the same thing here. This is 1 less than that, and this is 2 less than that. Okay. Now because this is implicit, the right side should be the index of the highest y I used on the left. If I start from I plus 1, then this should be x plus 1 y I plus 1. If I start from I, then this should be I minus 1, this should be I minus 2, and this should be I and I. Okay? So in the implicit method, the right side is always the highest index of the left side. Alright, so let's plug in y, let's plug I equal 2, 3, 4, all the way to the end. Why start from I equal 2? Because if I start I equal 1, then it becomes y 0, and I do not have any 0 index. My index always starts from 1. So the minimum I can put in here should be 2. What is the maximum I can put in there? Well, the final point is yn and xn, so the maximum I is going to be n minus 1. That's why I start from 2 to n minus 1. For every I we put in here, we rewrite the equation. Let's say for I equal 2, we get 3y2, 3y3 minus 4y2 plus y1. Okay, and then this is taken to the left side, so it's minus 2 del x times f x1, y1. Well, I start from 2, right, so it should be 3. So minus 2 del x f x3, y3. That's exactly what we have here. You can continue doing this by plugging I equal 3 all the way to the end. So at the end of the day, we get n minus 2 equations, right? N minus 2 equations. How many unknowns? Well, we have y2 to yn minus 2. From y2 to yn minus 1. Well, but the unknowns actually were y2 to yn. So we have n minus 1 unknown here, but n minus 2 equations. There is one equation less than unknown, so what should we do next? That means we're missing one extra equation. So in the next video, I'll show you how we can basically add one more equation to make it n-1, n-2 equations, n-2 unknowns, or n-1 equations, n-unknown.